Ana Moraes, and I'm the Deputy Director of the Wonderful Institute for Sustainable Engineering. And I want to welcome everybody to Undergrad Research Symposium today. But before we start, we would like to give the honor cords to some of the undergrads and grad students who are graduating this semester.
So as we call your name, if you'll come up, I'll grab the cords and we'll put them around your neck. So. Okay, we'll do the undergraduates first. The first one is Abby Peters. And the next senior that's graduating is Carly Barlows.
All right, so the next undergraduate researcher is Sarah Walsh. And the last undergrad researcher is Evanna, Dominic.
Alrighty, hello everyone. Super happy to be the first presentation. So did you all know that 90% of refrigerants are hydrofluorocarbons, but less than 3% are actually recycled? Hello everyone, my name is Evanna Dominic, and today I'll be presenting about experimental solubilities of refrigerant mixtures, specifically HFC 32 and 125, using the ionic liquid EMim TF2N. Here is a table of contents, kind of the overview of my presentation. But the objective of this presentation is to discuss a comparison of binary solubilities for our refrigerants in the ionic liquid using a variable volume view cell, or a VVVC. And we are going to measure ternary solubilities for R410A, specifically composed of HFC 32 and 125 in our ionic liquid using our variable volume view cell. So specifically, why are we measuring these solubilities? Refrigerants like R410A are difficult to separate due to their components having similar boiling points. As a result, conventional methods of separation like distillation are ineffective and they don't help with separations. So as a result, we use extractive distillation where we rely on a solvent or an ionic liquid to help with this. And currently, most of our research focuses on binary systems with one refrigerant and one solvent, but real systems like R410A are ternary mixtures where they're comprised of two components like HFC 125 and 32. And so the question of our research is, do ternary systems behave the same as what we predict from binary data? And by understanding this more, we're able to learn more about separation technologies, but be able to help us with effective separations. And for our methodology, we use a variable volume view cell, or VVVC. Here we have our refrigerant and ionic liquid that we put in the cell. And our liquid component will go to the bottom of the cell and our vapor component will go to the top. And then we are going to be monitoring our temperature and pressure conditions to make sure our system is at equilibrium. Once these conditions are reached, we will sample both the liquid and the vapor phase, and we'll send this to the gas chromatograph, which you can see here. Using our gas chromatograph, we get our area counts, which we convert those to moles and then to mole fractions. And then from there, we're able to calculate our solubility and selectivity, which will help us to understand more about these refrigerants and allow us to do better in terms of our separation capacities. And here we take our measurements from 0.1 to 3 megapascals at our three isotherms of 25, 50, and 75 degrees Celsius. So now onto our results. Here we are comparing our binary system solubilities. So as you can see from the graphs, we have our pressure and our mole fractions for our two components for R410A. Here we have HFC 125, and here we have 32. And here you can see the various pressures that we test, but also our temperatures. And here we're doing a comparison of previous works. Here we have the PETPA data, which you can see with the blue square, our VVC data from this work, which is the red circle. And then we have the IGA values, which are the triangle, and then our Pang-Robinson equation of state, which is this work. And so based on these comparisons, we can see that our binary solubilities are consistent with our literature values, but also we can see that our solubility will increase with pressure and decrease with temperature. And our higher solubility values are exhibited for HFC 32 in this ionic liquid than EMim TF2N. This data is helpful because it allows us to understand which ionic liquids have the best solubility in terms of separating this refrigerant mixture. And then we're able to look at our ternary system solubilities at 298.15 Kelvin or 25 degrees Celsius. So on this axis, we can see the mole percent for our ionic liquid. And then we can see here our composition for HFC 125. And then on our bottom axes, we can see the composition for HFC 32. And here we can see our feed, our ternary liquid phase, ternary vapor phase, and binary vapor liquid equilibrium data denoted by these symbols. And all of these measurements were taken at 298.15 Kelvin. And we're also able to use the binary system ideal mixing rule over here, which basically, in theory, would allow us to predict the ternary system solubilities based on the binary system solubilities. And here we can specifically see the solvent to feed ratio information. And then we can also see that as pressure increases in isotherm conditions, the solubility will increase about 60% more in HFC 32 than in 125 in this same ionic liquid. Additionally, we're looking at our ternary system selectivities. So we can see here with our temperature and our selectivities that our selectivity will increase with our increasing temperature and it'll decrease with our increasing pressure. Selectivities are important because it allows us to better understand the ability for the ionic liquid to be selective to each of the refrigerant components, helping with separations. And then we're also able to look at our solvent to feed ratio at various pressures. And we can see here with increasing pressure, our solvent to feed ratio increases, or decreases, my apologies. And then with increasing temperature, our solvent to feed ratio increases. So in conclusion, using our variable volume view cell, we're able to effectively measure our solubilities of our systems, but the binary system will not always be able to predict our ternary system solubilities based on our high pressure and temperature conditions. And our binary system solubilities were consistent with our literature. And our ternary system solubilities will provide us with more information, such as the solvent to feed ratio. And this will indicate the overall effect of this ratio on solubility as well as selectivity. And overall, this will help us with improving recycling of refrigerants and overall improve our separation capacity. In the future, we will model various ternary systems using thermodynamic models, and we will apply our ternary system solubilities using rate-based models of the extractive distillation system. I would like to thank Dr. Shiflett, Dr. Skirdo, and Julia, my mentor, and the National Science Foundation for the Engineering Research Center, or EARTH. Thank you all for your time. Does anyone have any questions?
Oh, okay. Hi, everyone. I'm Leah. And I'm Sarah. Okay, yeah, it works. I'm Sarah. And today we're going to be talking about energy efficient separation of hydrocarbons from hydrofluorocarbon refrigerants using PPO and PDMS membranes. So today I'm just going to talk about our motivation and introduction about why we are doing this research project and our goals and approach to using membranes to separate out refrigerants, the chemicals that we use and how we're testing these and the results that we have found so far, some general conclusions and what we're going to work on next. So just to start, refrigerants. They're everywhere. We use them in a variety of processes and industries, air conditioning in here today, so we're all nice and cool. Food and beverage processing for amazing food right over there. Pharmaceuticals and chemicals. But currently our recycling methods for these refrigerants are incapable of separating these azeotropic or near azeotropic mixtures, as our current refrigerants are made of hydrofluoroolefins, which are HFOs, which have a low global warming potential, hydrofluorocarbons, which are HFCs, which have a high global warming potential, and hydrocarbons, which are HCs, which have high flammability. So basically what we're trying to do is we're trying to separate out components to recycle and repurpose those HFOs and HFCs while getting rid of those hydrocarbons from these mixtures through synthesis and use of our membranes. So a good way to model this and how to think about this is looking at the refrigerant gas R422B, which is made of isobutane, which is a hydrocarbon, and then HFC 125 and HFC 134A. So our goal is to use membranes to filter out that isobutane so that R125 and R134A can be further separated and recycled accordingly, and we can get rid of that hydrocarbon in there.
So now to dive a little bit further into kind of our goals, specifically for the research we're doing and our approaches. So we have been synthesizing polymers to create the membranes and synthesize the membranes. And then we're also looking at commercially available membranes as well. So we're kind of have two different approaches there. And then once we have the membranes, we perform some tests to determine the permeability and selectivity of these membranes for a variety of gases. And then eventually, currently we're working with single gases. Eventually we will evaluate the performance with real refrigerant mixtures and eventually scale up to hollow fiber membranes instead of just kind of the flat disk membranes that we're working with right now. So we are using two main chemicals or polymers to synthesize our membranes and test our membranes. So the first is PPO, and the full name is there, but you guys can read that. And the molecular structure is also on the screen. But we initially chose PPO for its potential favorable interactions with the hydrocarbons. That is kind of what we expected to see, is that it would interact differently with the hydrocarbons than some of our refrigerants. However, we'll get into results in a little bit. That is not necessarily what we saw from our results, but that was kind of the initial intent. We synthesized this membrane with a solvent called NMP. And so far, we have performed single gas tests with HFC 32, HFC 125, propane, and isobutane over both 4 and 24 hours to evaluate steady state. Yeah.
The other membrane component that we like to use right now is PDMS, again, really long name up there. You guys can all read. And we really like this because it's commercially available, and there's also been lots of testing done on it prior to this. So we have comparable literature data, and also we can obtain a lot of it, so we can do multiple tests. We also like it for its high permeability overall. We think that that is very ideal for getting a good selectivity. You need high permeability, so it's more effective. And so with this, we've done single gas tests at 35 degrees Celsius and 50 degrees Celsius for HFC 32, HFC 125, HFC 134A, HFO 1234YF, propane, and isobutane. Another thing we really like about PDMS is not only is it commercially available, but we can also synthesize and modify it here in-house. So what we're also working on is synthesizing our own PDMS and seeing if it is comparable to the commercially available one, so that we can start to modify it with hopefully ionic liquids to increase the selectivity of the permeability of these membranes.
Wonderful. So now to take a second to talk about kind of how we're synthesizing these membranes. So we talked about PDMS, that's kind of what's in the purple box. And that is for the kit that we're using to synthesize the PDMS ourselves. So it comes with a base, and then the solvent we use is N-hexane, and then we add a cross-linker, do quite a bit of stirring, which you can see kind of on the bottom graphics, and then that is ultimately how we synthesize our membranes. And then in the green, you can see our PPO, which has the molecular structure for NMP as well. But the synthesis process is very similar for both of those membranes, and ultimately after they are dried and the solvent evaporates off, then we're able to test them in our static membrane apparatus, which is kind of represented by that red graphic that you see on the bottom. And then on the right side of the screen, you can see examples of what our casted membranes look like. They're transparent pretty much, but these are ones that look particularly good, so we'll continue to make our membranes in that way. And then here are the gases that we use. So we've listed them off a few times now, but there are all of the molecular structures of these gases. And then we also have listed the kinetic diameter of these gases. Initially, one of our hypotheses is that the permeability would depend on the kinetic diameter. However, we'll see in our results in a little bit that is not necessarily what we observed when we performed our initial testing. And then finally, we have our testing conditions. So again, here are the refrigerants and hydrocarbons that we tested, but we tested at a pressure of 2 bar, temperatures of 35 degrees Celsius and 50 degrees Celsius. And then there we also have listed our kind of average membrane area and thickness of these membranes. We're looking at between like 100 and 130 microns. And then there we also have our equation for permeability, which is kind of our main result from these tests. But kind of the important thing to note there is that permeability is a function of temperature and pressure, and so that's something that we are looking at as well. So here are initial results for PPO. So we tested again at 4 and 24 hours, primarily to ensure that after 4 hours, we were reaching our steady state value of permeability. So as you can see, green, purple, and blue, those look very similar between our 4 and 24-hour tests. However, the main difference is with that red block, bar, I guess, and that represents our propane. So that just tells us that after 4 hours, propane had not yet reached steady state. But for the most part, the 4-hour mark was appropriate to complete this testing. So as you can see on the y-axis, these permeabilities are very low. So it looks like there's kind of a big difference between the HFC 32 and isobutane are a little bit higher, and then propane and HFC 125 are a little bit lower. However, if we were to kind of match that to the scale we'll see when we look at PDMS, these are all very similar. So because this permeability is so low, it limits the effectiveness for separation because they are relatively the same on the same order of magnitude. So that led us to conclude that PPO is just generally not suitable for the application that we are applying in this study. And then we also have our selectivity here. So the selectivity is still significant, but again, because the permeabilities are so low, PPO is not suitable for these applications.
This is why we like PDMS. So here are some of our results from our PDMS membrane. As you can see on our graph, the permeabilities are way higher, which is why we really like this. This is the commercially made PDMS that we have tested, because the ones that we have made in-house are not, we finished those in the past weeks. We have not gotten any tests done on those yet. But this is at 35C. You can see that the hydrocarbons, so propane and isobutane, have a high permeability compared to those hydrofluorocarbons and the HFO. And so originally, like how we said, we expected some size selectivity, and this proves that that is not actually necessarily a big factor in that, and it's more about affinity. So our HFO and HFCs are fluorinated molecules, and our hydrocarbons are not. And so from this data, we can reasonably conclude that the fluorine interactions with the PDMS drive a lot of these permeability results. We also have our selectivity in comparison to our hydrocarbons, specifically isobutane, because that has our highest permeability listed in this table. So for HFC 32, it's 3.41. For HFC 125, it's 11.9. HFC 134A is 4.85, and HFO 123YF, it is 4.59. And also these tests have been done in duplicates to make sure that we are doing consistent performance throughout. Because PDMS has been so promising, especially with those high permeabilities, we also wanted to test the temperature effects of the permeability. So on this graph, the left side values are what we just saw above at the 35 degrees Celsius point, but on the right side, it's the 50 degrees Celsius point. And you can see as temperature increases, the permeability decreases, which answers a lot of questions that we had with membranes. We were trying to see if solubility or diffusivity was going to be a main driving force for our permeability. And we can conclude that it's solubility more so than diffusivity, because diffusivity increases with temperature. So if it was more dependent on diffusivity, those values at the higher temperature would be higher. And since it's not, we can conclude the solubility drives these interactions more. But those results will also be confirmed or tested later when we're doing further work with solubility and diffusivity of our membranes in the ZMIS in our later works. So basically, in conclusion, we have produced PPO and PDMS membranes and completed single gas tests with HFCs, hydrocarbons, and HFOs. And we're going to move forward with the PDMS research because it's had a lot of promising results and adequate selectivity compared to the PPO.
And then moving forward, we will complete our testing at 50 degrees C, getting those duplicate data points completed. And then next steps are to compare our commercial PDMS membranes to our synthesized PDMS membranes. So that is up next, is throwing those in the static membrane apparatus. And then moving forward, we would love to be able to modify the PDMS, specifically the one that we're synthesizing with the kit, specifically by including ionic liquids and seeing how that affects selectivity. And then, like Leah mentioned, we will look into solubility and diffusivity studies using our ZMIS. And then later on, we will look into hollow fiber works and testing, and hopefully using those applications. We want to give a huge shout out to Univa, our mentor, and Dr. Shiflett. They've been so helpful in our understanding of all of this and the research we are completing. So thank you so much. And then I think that's all we have. So thank you, and we'd love to answer any questions you have. Yes.
For 29. That one. What's the order of kinetic diameter on those?
That's increasing, but let me go back to kinetic diameter.
Increasing, or is it? I don't remember.
I don't think it's strictly increasing. So that would be a good thing to add to that graph so we can kind of better see the relationship there.
Yeah, I was just kind of curious what happens if you plot the permeability versus the kinetic diameter to see if it's purely like a size exclusion membrane or if there's actual interactions going on.
Thank you.
So what kind of safety precautions did you guys have to take with the reagents you worked with and the experiments you did?
Yes, so we always used appropriate PPE when we were synthesizing our membranes. So that always include gloves and lab coats and goggles. But kind of a notable safety measurement that we've taken more recently is with our static membrane apparatus. Because we were testing so many different gases, we have kind of changed recently the way that we were testing that, and we are purging the system with nitrogen in between each gas just to make sure that there are no gases going into the static membrane apparatus that could get in there and we don't want it to, or kind of damage the system. So that is one more recently. Is there anything else you could think of?
Also earlier in the semester, it just didn't produce promising results, so we didn't put it on here. But we worked with chloroform, and so we used some really specific gloves and PPE to make sure that since that is a carcinogen and could knock you out. We were really careful with that one. We also have moved hoods to make sure we have adequate ventilation because we are working with a lot of solvents that are could be very harmful.
Dr. B.
So you mentioned with regards to the separation process, there were two possibilities where it's either solubility or diffusivity, right, for separating everything out. Can you just talk a little bit more about that?
Yeah, so permeability can be calculated by using the solubility and diffusivity measurements. And so basically with our future works with the ZMIS is what we're going to try to do is calculate those solubility and diffusivity, separately, and then get a, and like a, what's the word? Oh, an ideal permeability. And then we're seeing like how that actually like works real, but like in real world situations with what we're actually getting with our real data. But so permeability is a function of diffusivity and solubility.
How are you measuring solubility? Because that's like, because I'm the way I'm hearing it for your system is that your solubility is you have these gaseous molecules that are traveling through a solid material. Okay. And so what is solubility in that case?
So whoa, sorry, that was really loud. Solubility is going to come from our future works in the ZMIS. We're concluding reasonably that it is solubility that's driving the permeability because if it was diffusivity, it should have increased permeability with temperature because diffusivity increases with temperature. So that's just a conclusion that we've made without actually measuring the solubility, and that's what we're working on in our future works.
Cool. Thank you.
Great presentation. All right, so our third speaker is Madeline. Where is she? Yeah. And she's going to talk about interfacial tension measurements of refrigerants, EGFC 32 and GFC 125, in a mixture with ionic liquids, EMim TF2N.
Hi everybody, my name is Madeline, and today I'm going to be presenting my research on interfacial tension measurements of refrigerants HFC 32 and HFC 125 in ionic liquid EMTF2N. So the goal for today that I want to present for you guys is going through the objectives as well as the background, next talking about the methodology and how we obtained our data, and then finally going through our results and our discussions and our future work. The goal of this project is to measure interfacial tension of refrigerants HFC 32 and HFC 125 in mixtures with ionic liquid EMTF2N using a pen and drop method. So why do we care about the interfacial tension of refrigerants in ionic liquid systems? Many refrigerants are azeotropic, meaning that they have the same boiling points and cannot be separated using conventional distillation systems. A promising solution to this is extractive distillation using ionic liquids, which can selectively separate components, making refrigerant recycling easier. These current models assume thermodynamic equilibrium and that these systems exhibit ideal behavior. However, this does not capture mass transport limitations or mass transport phenomena such as interfacial tension. We are able to measure interfacial tension using a pen and drop tensiometer. In a pressurized cell at isothermal conditions, we can inject the ionic liquid into the view cell, which can be seen in here, to create a suspended liquid drop. Next, we are able to inject the vapor continuous gas phase into the cell, which surrounds the ionic liquid drop. Then the system is then allowed to reach thermodynamic, mechanical, and mass transfer equilibrium. Once this equilibrium has been reached, we can take the temperature and pressure at these temperature and pressure conditions to measure the densities of both the liquid droplet as well as the continuous gas phase. These densities, as well as the droplet profile, are inputs into a software that iteratively fits the Young-Laplace equation to the droplet profile. If the droplet profile does not if the temperature and pressure conditions do not satisfy the Young-Laplace equation, we can adjust the tip size in order to create a more round droplet profile and satisfy the equation. Here you can see a schematic of what I was just currently presenting on. You can see the refrigerant cylinder here, as well as the computer and the camera where we are able to view the droplet profile, as well as where we inject the ionic liquid with the syringe here, and then we use a syringe pump to pump it into the system. So one main key takeaway from our results that we found, or from our methodology, excuse me, is that we found that tip size greatly affects measurement precision when it comes to the droplet profile. So what we found is that at lower tip sizes or smaller tip sizes, as you can see here, we create more linear profile, which is good because the pendant drop method relies on the Young-Laplace equation, which means that if our tip size is too big and that the equation is not satisfied, then our data is not necessarily super accurate. And so when we reduce the tip size, we get more accurate interfacial tension measurements. First, to validate our system, we measured the surface tension of pure EMTF2N at varying temperatures. As you can see here, the blue squares represent our data against current literature data. We found that surface tension of EMTF2N currently aligns with literature trends presented and decreases with temperature. Additionally, we found that surface tension decreases with increasing temperature, shows minimal dependence on pressures ranging from 1 to 30 bar. However, as we decrease in temperature, as you see here, surface tension decreases. So the blue right here is the 25 degrees Celsius, and then the green is the 50 degrees Celsius, and then the orange is 75 degrees Celsius. Next, we were able to measure refrigerants HFC32 and EMTF2N and HFC125 and EMTF2N. Our results showed similar trends as stated before. So as we increase in temperature, the interfacial tension decreases in both of our systems. Additionally, the interfacial tension decreases with increasing mole fraction of both HFC32 and HFC125. As you can see in this graph here, our predicted values currently used in thermodynamic models greatly underpredicts the interfacial tension that we exhibit in our experimental data. As you can see for the HFC125 and EMTF2N, the predicted interfacial tension values of the ideal mixing greatly overpredict what we have seen in our experimental data. So what can we conclude from this research? The main takeaway is that both of these systems deviate from the ideal mixing rules currently assumed in thermodynamic models, which means that these models are not accurate representations of how we can recycle refrigerant efficiently. We also found that interfacial tension strongly affects mass transfer phenomena, which means that lower interfacial tension improves wetting and reduces required packing height. Additionally, we found that as we increase mole percentage above 20%, the interfacial tension deviates significantly from the ideal mixing rule. Future work is going to extend to the refrigerant HFC 134A to evaluate whether these similar trends persist that we've already seen. Secondly, we are going to use simulations using PSAF to predict phase behavior and support experimental validation. I would like to thank Dr. Shiflett as well as Dr. Scrudo and Julia for their guidance for this project, as well as National Science Foundation for funding this project. Thank you. I'm sorry, could you repeat the question? Sorry. Oh, we were using nitrogen. Yeah, we actually use we use nitrogen because it's an inert gas, so it doesn't mix and like interact with the ionic liquid, and air is actually bad for ionic liquid, so we don't use that. So that's why we use nitrogen in these systems. Yeah. I'm not entirely sure, but I would love to look into that and get back to you.
Can you go to slide, I think it's 10? Yeah. Okay. This is a tough question. So in the case of HFC 32, when you look at the prediction versus the measurement at, let's say, 348, the surface tension's higher, the experimental surface tension is higher than what you would predict from the ideal mixing rule. And then when you look at 125, the surface tension is lower than what you would predict from the ideal mixing rule. So do you have any thoughts about why in one case with 32, it's experimentally higher, and in the other case with 125, it's experimentally lower?
That's a good question. I think it has something to do with the fact that this ionic liquid specifically is more selective for HFC 32 rather than HFC 125.
So therefore, there would be maybe more 32 dissolved in the ionic liquid than in the case of 125. That's plausible. I think something else that could be happening, I saw this recently in some molecular simulations. In one case, the 125 wants to be at the surface of the drop and not so much in the center. And in the other case with the 32, the refrigerant wants to be in the center of the drop and not at the surface. So you might think about that, because I think that plays a role in the surface tension, because it's kind of what's going on at the surface, which is why you measure the curvature at the surface. So maybe think about that too.
Are these experiments repeatable? Did you have more than one data set for each isotherm, or what do the error bars on those look like?
I'm not entirely sure.
The deviation from non-ideality, that correlate with deviations from non-ideality? Or, because viscosity is an important factor with surface tension too.
That's a really good question. I'm actually not super sure. I can look into that and get back to you. But yeah, I mean, if Julia wants to answer, no, okay.
Yeah, so, but I mean, yeah, if we have the available viscosity at those temperatures, maybe Diego has those, because I mean, I don't know. But yeah, so yeah, it will be very, very interesting to see how it deviates as well from the viscosity. Yeah, yeah, it will be nice to see. Okay.
So Madeline, I was just curious, you've talking like you're doing a lot of interfacial tension measurements, which is really cool and exciting. So what I was curious about is just because you're tying it together with mass transfer, which of your results directly relates like interfacial tension with mass transfer?
That's a good question.
And if it's not up there, that's okay. I'm just curious like what it is.
Up there, but we do know that interfacial tension is a transport property, so it is influenced by mass transfer limitations that can be seen in shock distillation.
Okay. Thanks, Madeline.
All right, so our next presentation is going to be given by Elizabeth, and it's going to be about removing a model contaminant from water using activated charcoal encapsulated in hydrogels for an undergrad learning experiment.
All right, cool. My name is Elizabeth Auberly, and today I'm going to be talking about removing a model contaminant from water using activated charcoal encapsulated in hydrogels for an undergraduate learning experiment. So looking around the room, raise your hand if you own any blue clothing in your closet.
Okay, hopefully this should be everyone since we do go to KU. But what many people don't know is that industrial dyes, such as the dyes that we use to color our clothing, actually have a really large negative environmental impact on local ecosystems. One notable industrial dye is methylene blue, which is the one that's used to color a lot of our blue clothing. This is mostly prevalent in the countries that are shown above, which have really high textile production rates, such as India, China, Vietnam, and Bangladesh. So during the dyeing process, about 10 to 25% of the dye is actually lost and does not enter the clothing. Out of this 10 to 25%, this leftover is discharged into the environment in effluent concentrations of about 200 to 500 milligrams per liter. This is extremely notable as the toxic threshold is about 10 milligrams per liter. So this is about 20 to 50 times what we would hope to be discharging into water. Some other negative effects are that this dye is carcinogenic, toxic, can reduce the natural biodegradation in the water, and also cause secondary pollution. The main thing we are focusing on is the fact that it reduces the visibility of the water. So when the visibility of the water is reduced, this can reduce how much sunlight reaches the vegetation at the bottom of the water, which then decreases the rate of photosynthesis and also impacts the amount of dissolved oxygen that's in the water. Because of the decreased dissolved oxygen, this can also kill a lot of aquatic organisms and have a big impact on the ecosystems. I apologize. And so obviously as engineers, we are tasked to solve a lot of problems like this. And so therefore, we want to look into how we can implement these environmental concepts into our undergraduate curriculum. So as of right now, some of the only ways to get involved with environmental applications within the chemical engineering department is either by getting involved in research, or you can actually dive a little bit out of the department and take some civil and environmental engineering classes. And so we specifically want to find ways that we can implement these environmental applications and do stuff specifically related to chemical engineering, such as reaction kinetics, thermodynamics, and process design, even looking at wastewater treatment plants and such. This would be a really great experiment that we'll talk about in a second to implement into classes such as 111 and 112, where students are first diving into chemical engineering and learning about the specific things they'd be interested in the broader category of chemical engineering. So to be able to actually implement this into a class, we want to have a specific choice of materials and start looking into those logistics of how we can make this safe, non-toxic, and cost-effective. So the first thing we're going to look at to be able to put into the curriculum and experiment is activated charcoal. So activated charcoal is a very effective and also commonly used contaminant removal device. And that is because it has really large, or it's very porous. It has really large surface area, which makes it a really good site for adsorption. However, because activated charcoal is a powder, it can be oftentimes hard to remove after it's used in a system and can even take more advanced technology. Therefore, we want to have a way to physically encapsulate this activated charcoal, which is where our hydrogels come in. So looking at our hydrogels, these are sodium alginate strands as pictured above. The activated charcoal molecules are going to weave their ways into the little pockets of the hydrogels, which will eventually create our activated charcoal encapsulated hydrogel. And so this gives us our way to have that physical encapsulation and make it a lot easier to remove our activated charcoal hydrogels at the end of a process once they are in their mediated water. So as for how we're actually going to put this into an experiment, we have developed a procedure where we can create this in lab safely and effectively. Our first step is mixing the sodium alginate with activated charcoal, and we are then going to pump this into a curing solution like calcium chloride. This is going to sit for about 15 minutes until the beads become kind of like little Orbeez or boba, if you know what that feels like, but they're essentially kind of just little jelly beads. So once we have those, we are going to put them into a contaminated water sample. In this case, we are actually going to use food coloring instead of industrial dye like methylene blue, and that's just for safety purposes and also being able to have safe disposal of something like this, and again, keep it, non-toxic and pretty simple for our undergraduate experiment. So what we'd expect to see is our remediated water would have much less dye in the end, and we can see that in a little bit. But one thing throughout this experiment as well is that throughout the trials, which take about 7 to 8 days, we measure the absorbance values using a spectrophotometer, which then using a calibration curve will turn into concentration values. And so, as I said, we did see some results from this. So this is our picture of the original initial dye in the water. And over time, which is about 7 days, you can see that the dye significantly decreased, and actually we almost had pretty much clear water. This is really great for an undergraduate experiment because not only are you able to collect data, as we said earlier, but you can also see visible and tangible results of the work that these students are doing. So again, we do need to still gather data to make sure it can be reproducible. And so this is our preliminary removal curve. This curve was taken using 9 different trials, and this specific data was taken over the span of 8 days. So as you can see above, we reached about 98% removal, which is super promising, especially for future experiments. And we also had a very low standard deviation, so really insignificant error here, which means it can be very reproducible and also allows to have very good control experiment and leave a lot of potential for testing out new variables. So the first variable I decided to test was the concentration of activated charcoal and how it impacts the removal percentage. So starting off with 5 grams per liter of activated charcoal in sodium alginate, you can see it plateaus at around 30%, where it reaches its saturation and is no longer able to absorb any more dye. The 10 to 20 grams per liter, you can see they both have really good absorption capabilities. And because this was a 7-day trial instead of 8, they got up to about 90 to 95%, but overall the data is really consistent with our control trial. We can see some little differences between the 10 and 20 grams per liter, and because we aren't agitating the solution, there could be some different contact between the dye molecules and our activated charcoal molecules, which could create a little bit of a difference. Again, we had a really low standard deviation and really insignificant errors. So again, something you could definitely mess with in an undergraduate lab and have some good results that are don't have a lot of variability. So overall, our experiment is simple, reproducible, and has a variety of variables that can be tested. It's cost effective, safe, and non-toxic as well, which would work really good, especially in an early chemical engineering class, such as 111 or 112. We got some solid results in our control trial proves that we would be able to test out a lot of new variables as well. One thing I would like to focus on in the future is adding agitation. As I said, our trials are about 7 to 8 days long right now, which is not implementable into a lab currently. So being able to mess around with agitation could speed up the rate of removal. We'd also look at the initial concentration to bead ratio and see how we can still have high removal rates while decreasing the amount of time that it takes into a standard lab time of around 2 to 4 hours. So overall, this experiment is super promising and I would love to work on it in the future. It's a great connection between environmental and chemical engineering, and I'm super excited to keep working on it. So thank you guys. I would like to acknowledge Dr. Bertuccio and the Bertuccio Research Group, as well as WISE, CMPE, and everyone who came out tonight to support. So thank you guys, and I would love to answer any questions. Yeah. Yeah, so essentially what we did, we just use it's pretty much just like a mixer. Like it's like a blender normally. And so I made our like sodium alginate mixture, which is just water combined with like our sodium alginate powder. And then once I made that into kind of like the like gel substance it is, then we just added the activated charcoal and also blended that up. So it's pretty much just like a black type of sludge, which you then like cure. Yeah, so super simple on that part. Yeah.
But like, how do you make the ball of?
Oh yeah, so we'll like here. I can go back. Oh wait, I guess it's already on here. So once we have that kind of like gel with the sodium alginate and activated charcoal, all you're gonna do is add it to like our curing solution, which is like the calcium chloride in this scenario. And so it's just gonna have like a cationic exchange, which is then gonna turn it into like a solid like gel bead. Yeah.
Have you guys thought about trying to publish it in like a education journal?
No, not really. This is the first semester that we started working on this. I kind of transitioned from some drug delivery experiments to decide to do like environmental applications. So I'm kind of the first person that's worked on this. So obviously want to keep working on it in the future, but haven't started looking at any publication yet.
Yeah, there's a journal called the Journal of Chemical Engineering Education. And it'd be neat for you guys to publish some of your experiments in there so that other people can see like these could be experiments used in like their 111 or 112 class.
That'd be really cool, for sure.
Okay, good.
Have a consistent particle size?
So usually, I guess we looked at this a little bit in the past with like the drug dealer research. I didn't specifically look into it with here, but we expect it to be like want to say 3 millimeters, I believe, is kind of data I'd taken in the past, but not exactly the same every time. And I can't exactly like say off the top of my head for this specific experiment. Yeah. Do you mean like the part, like the size, like the bead? Is that what you mean? Okay. Yeah, I think it like the size could obviously like change it. I think it would change like the amount of contact, or like this is what I would imagine. It would like change the amount of contact between like the activated charcoal and like the actual food dye molecules, just because it would have like a larger surface area and like more space to interact and stuff like that. So like it could definitely be something that we look into in the future.
I have a question for you.
Yes.
Nice talk. Did you change mixing speed at all? Did you incorporate, or are the particles just suspended?
Yeah, so they're suspended for right now. I just kind of wanted to start with just like absolute like control data, like super long trials. And so agitation is something that we want to look at in the future. I did mess around with agitation a little bit, but out of like a 2-hour trial I did, I only got up to about 35% removal. And so that's definitely something we want to mess with in the future to be able to like speed up those trials and kind of change around the speed of agitation and, you know, see what happens with that.
So these particles are just sitting in a beaker
they're
and
just sitting.
no orbital mixing or
Yep.
anything? Okay.
7 to 8 days. And orbital mixing is something that we're looking into in the future. We don't necessarily have like the equipment for like this specific lab yet, but we're looking into it. We're getting there. So yeah.
More question for you.
Yeah, I got you. Great talk. Just while we're on the topic of like future stuff that you could work on, maybe it'd be interesting to look at like regeneration for this. Like if it's possible to get the methyl blue to actually diffuse out and then reuse the beads. I think.
Yeah. Yeah. So there's some research, nothing that I've done, but there's some research online in other different papers that talked about being able to put the beads into like a solid. Obviously you'd be able to have like safer disposal then, because you have a really high concentration of dye in like a smaller amount of liquid. So I haven't done any experiments or research on that yet, but it is something that has been proven to work in other people's experiments with methylene blue. Yes.
Have you kind of back to the particle size for the activated charcoal? Have you looked at like homogenizing that size or sifting it to make sure that you're using consistent sizing, because that can play a big impact on your absorption as well.
Yeah. As of
itself,
so as of right now, I'm using like super fine charcoal. So I mean, I've kind of trusted the process that yeah. You said what? Sorry. Yeah. Yeah, that's definitely something I look into the future. I haven't like messed with that yet at all, but obviously like right now I'm kind of just expecting that's like close to the same size, but that's definitely something that I didn't think about that could be cool to look at.
That's a quick one. When you put your beads in your dye solution, do they sit in the top or they get like well dispersed?
For like putting it into the contaminated water. Yeah. So they pretty much yeah, they kind of like sit at like the top of the solution for like the most part. I would like agitate just a teeny bit before I would take like the actual sample to test the absorbance. And that's just because I obviously want to make sure like all the food coloring was like mixed as I took the sample, but otherwise they pretty much just sit there. So again, looking at agitation, like that's something that I think could definitely change the scale and scope of this project. And so that could definitely change quite a bit of things and reduce the time from 7 days. Yeah, thank you.
So Welcome everyone. My name is Aditya Kulkarni,
And I'm Marina Johnson.
and today we are excited to share our latest research on refrigerant flammability measurements and optical diagnostics.
Here's an overview of what we are going to discuss today. We're going to start with the problem statement, moving on to the background, and so on.
Refrigerants are essential to modern life, but the refrigerants we have relied on for several decades have had a negative impact on the environment due to their high global warming potential. As a result, regulations are causing a large-scale phase-out, with over 80% of these legacy refrigerants being phased out over the next decade, creating an urgent requirement for alternatives. A major hurdle right now is that many of these proposed replacements with lower global warming potential introduce a flammability risk, which raises a safety concern for people and systems that rely on them.
We are focused on characterizing flammability for safety. In order to do so, we need to learn about pure component and blend flammability limits as well as their burning velocity.
All right, moving on to our primary objectives of our research. To address the flammability and environmental challenges, our first major goal was to engineer a reliable testing apparatus specifically designed to measure the refrigerant flammability. Once the equipment was operational, then we can focus on gathering the experimental data. And we looked at both single component refrigerants as well as various blends. We aim to analyze the optical data captured from this test to calculate the burning velocity, which is a critical metric to evaluate the safety of these substances. Ultimately, this comprehensive methodology is designed to establish a technical foundation required to safe design and classification of the next generation of refrigerants.
This is the apparatus we use to measure the flammability of refrigerants. The test vessel used to determine flammability limits is located on the left, and the burning velocity apparatus is on the far right. To perform a test, first we evacuate the test vessel. Then we add combustible gas that is mixed with air using our stir bar. It is then ignited by a high voltage spark. We vary the concentration of the gas until the mixture propagates a flame after ignition. The lower flammability limit, or LFL, is the minimum concentration of fuel needed to be considered flammable, while the upper flammability limit, or UFL, is the maximum concentration where there is not enough oxidizer to be considered flammable. The image on the right shows the 90-degree propagation that a flame must propagate in order for it to be considered flammable. The test can be conducted with various testing conditions by changing the temperature, pressure, humidity, or spark duration. The conditions we use typically are 23 degrees Celsius, 1 standard atmosphere, a 0.4 second spark duration, and 50% relative humidity. Here you can see the flame behavior near the flammability limits for HFC 32 and air. The LFL is shown on the left and the UFL is shown on the right. This is what our testing looks like to determine what breaks the 90-degree propagation, and the video on the right shows what our tests look like. As previously mentioned, one of our research goals this semester was to investigate the flammability of refrigerant blends. First, we chose to do a test mixture of HFC 32 and HFC 134A. We use this mixture because it's typically used as a benchmark to validate the apparatus, so it's a good case study for mixtures that contain one flammable component and one non-flammable component. We are most interested in the critical flammability ratio of these kinds of mixtures, which is the point where adding enough of the non-flammable component will render the mixture non-flammable. The CFR is shown here as the solid black line, and the dashed lines are the reproducibility requirement we are hoping to achieve. From our initial testing, it seems that our apparatus is reproducing similar results to those found in literature. In order to help guide future testing, we wanted to find a simple model that can be used to help predict upper and lower flammability limits for these mixtures. We applied the equation shown in the top right to predict the orange and blue lines shown on both graphs. The orange is for the upper flammability limit, and the blue line predicts the lower flammability limit. For now, we are treating the theoretical factor as a fitting parameter and simply fitting it to our existing data. Once the apparatus is benchmarked, we would also like to study mixtures of flammable components. This graph shows our preliminary results for a blend of HFC 32 and HFO 1234YF. Our experimental data is shown in red,
which represents the LFL and the UFL for the individual pure components. Using the data for pure HFC32 and pure HFO 1234YF, Le Chatelier's mixing rule can be used to predict the flammability limits for various mixtures of these two, which is shown by the dashed line. We've gone ahead and tested a 50-50 weight percent mixture of these components. As you can see on the graph, the equation fits well, although the UFL shows a little bit less agreement than related to the LFL. Le Chatelier's mixing rule has two main limitations. It can only be used for mixtures of flammable components, and you must have flammability limit data for each individual component. Fortunately, this data exists for several simple components already, so we can extend the rules to predict the lower flammability limits for mixtures of class 2 and class 3 refrigerants. For example, we calculated the lower flammability limit for mixtures of propane and several class 2 refrigerants. And from this graph, we are able to tell where these mixtures transition from class 3, which is highly flammable, to class 2.
All right, moving on. Now let's talk about the burning velocity. This is a fundamental metric for our safety evaluation because it essentially tells us how aggressive a substance behaves, specifically how fast it burns, releases energy, and spreads a flame. So the burning velocity is calculated using the equation shown on the screen right here. We utilize high-speed cameras to measure the flame equation shown on the screen. We utilize the high cameras to calculate the propagation speed, which is the physical rate at which the flame front travels up through the glass tube. We use the glass area ratio to account for the flame's curved dome-like surface within the tube. The total surface area of the flame front, AF, is calculated via image processing, while the lowercase af represents the flat cross-sectional area of the flame space. By multiplying the raw speed by this fraction, the equation allows us to refine our measurements based on the flame's actual shape and area. To get the flame surface area, we start with the raw images captured by our cameras. Using image processing, we first identify the outline of the flame. From there, we mark the flame profile with about 20 to 40 specific fitting points. The more, the better. Because propagating flame shape is too complex to be modeled by a simple geometric shape, we have to slice it up. As you can see in the annotated picture right here, we divide the flame into several horizontal sections labeled from X1 through X5. Breaking the flame down into these smaller segments allows us to calculate precise surface area. This brings to the next slide. The total flame surface area is simply the sum of the surface areas of all these individual horizontal sections. The image on the top right shows the precise measurements we pull from the annotated image, tracking the exact width and height along the flame's edge. You can see the specific formulas we use on the screen. We rely on the equation on the screen in the middle for the non-tip section where the bottoms are more level, and slightly more complex geometric formula for tip section if the flame happens to be a bit asymmetric. To handle this math efficiently, we developed our own custom software designed to automatically calculate the surface area across all these different sections. What you're seeing right now here is a snapshot of the tool in action. Now, for the sake of this presentation, and just to make the visuals easier to digest on screen, I'm showing a demonstration using just 10 data points for a non-tipped flame. In reality, we would follow the standard ISO methodology and plot 20 to 40 points. The software takes our inputs for each slice and computes the total flame surface area, giving us a value about 6,041 square millimeters for this specific run. Next, we bring all our variables together to find the burning velocity. We calculate the cross-section area of the flame space using the physical tube measurements, which is about 1,338 square millimeters. For the flame propagation speed, we calculate the velocity using a video tracking software, which simply tracks the physical distance traveled by the flame over the set period of time. When we plug those values into the main equation, we got a final burning velocity of 5.37 centimeters per second. Moving forward in our research, we will use this exact software process, but with more fitting points to get even more accurate results.
In conclusion, the flammability apparatus we use meets reproducibility requirements for mixtures. However, we would like to do additional testing to improve our confidence. Also, Le Chatelier's mixing rule shows good agreement with our experimental results for HFC32 and HFO 1234YF.
Additionally, our custom software automated the optical analysis and surface area calculations, significantly accelerating the research timeline.
In the future, our goals are to collect more data for HFC 32 and HFC 134A blends, as well as for binary refrigerant blends.
We will optimize the code to process the flame images faster and investigate optical measurement errors to ensure our model remains precise and reliable.
We would now like to take the time to thank Dr. Shiflett, Kevin Turner, and Ryan Dahl.
Thank you for listening to our presentation. We'll take questions at this time.
So you mentioned, so you've got a system for measuring the burn velocity, right? So, and I might have missed this. How many different mixtures have you looked at thus far?
So we just finished building the apparatus, I believe, like 2 weeks ago, and the video you saw, we got that last week. So we haven't really started testing with the proper methodology, and the example you just saw was just a demonstration of the software working and how we are planning to do, but we'll soon start with the experiments.
Great. All right. So now what I want to do is I want to ask, like, what do you hypothesize if you're trying binary mixtures? Like, what do you think is going to happen to the burn velocity as you increase one versus the other thing? What might happen? And keep in mind, like, I don't know the answer to this, so like, you can tell me whatever you want, and I'll just say like, yes, okay.
That is a good question. I think that I don't know. I think it will depend on what we're using, but I haven't done a burning velocity test, so I'm not quite sure what it will look like. But
I'm not sure as well. We just got the apparatus running. Yeah. So we would want it to spread slower and not be like an explosion, basically.
yeah, yeah. I think it would definitely impact the flame like propagation if it's not well mixed, but we have it stirring the entire time. So the goal is that it's well mixed. We could definitely try to stir it like for a longer amount of time to see if the flame like propagates differently depending on how well it is mixed, but we have not tried that yet. Yeah, we have a stir bar at the bottom. I'd say once we start putting air in, so I'd say it stirs probably like, it depends how many components we're adding as well, because it takes a while to like switch the tube to add the components, but I'd say about 15 minutes it stirs, 20 minutes. Yeah. I have not. Have you? No, we have not done that. Yes, thank you.
So my question again is around safety. Since you're purposely setting things on fire, what kind of safety precautions do you take?
Yeah, so when we're setting everything up, we use gloves so that we're not like touching anything, but also if you go back to the flame is in like a wait, go back one more. One more. It's in, like, it's confined. If you see in the actual picture, it's like not out in the open. I don't know how to say that, but yeah, we basically, like, we stand away from it. And we do have a vent. It's right on top. You can see it in the picture that's like the real picture. And we vent right away after the spark ignites.
And have you had anything unexpected happen?
Honestly, I don't think so.
Nothing that exploded or?
Oh, nothing too exciting yet.
I have a question for you. How do you think incomplete combustion would affect your flame front or even your flammability results?
I think the propagation again would be affected probably. Like, I guess I don't understand your question maybe completely. Can you say that again?
So if the gas that is ignited, if it doesn't go 100% to what you desire, like heat dissipation, maybe it goes to coke or a carbon, how would that affect your flame front? Or if it doesn't get, if actually if the gas doesn't even, if it doesn't if it partially even reacts.
Yeah, I think that the flame propagation would be different, but we do use like the same spark duration, so I think that it should be the same for each one because we use the same like seconds of for the spark duration.
On your apparatus, on the spherical vessel on the left, the way that's designed is if the vessel were to explode, if the top relief couldn't go, then everything is designed to blow out of the bottom. The walls are metal, and then the top is metal, and the bottom is just like real weak insulation. So on the flame front apparatus on the right, what have you guys done? How is that designed if the tube were to blow up without being able to vent in time off the top? What happens in that box? How does that eventually fail?
Kevin, can you help? I did not build it, so I'm not sure.
It's a good safety concern. This is part of the reason we don't have a whole lot of burning velocity data currently. We need to incorporate like a loose panel on the right one as well, because that is a concern. Because currently like, nothing's stopping it, which is not good. But we're working on it.
Yeah.
All right, our next speaker is Kinsley, and she's going to talk about the effect of compressed CO2 on the hydrocracking of polyethylene.
Hi, everyone. My name is Kinsley Holdman, and I will be presenting on the research that I help with today and specifically talking about the effects of compressed CO2 on the hydrocracking process of polyethylene. So, wrong direction, sorry. So this is our outline for what we're going to be talking about today, but let's just hop right into it by first discussing why is it that we should care about plastic pollution. Well, plastic production continues to grow rapidly with tens of millions of tons produced each year. And this number is only expected to increase within the coming years. And of those plastics, polyethylene specifically is the most widely used within the United States. So this presents a major problem for us as polyethylene will accumulate waste within the environment due to its difficulty to be broken down. So the goal of this research is to look at how we can convert polyethylene by recycling it into useful products such as fuel applications using a catalytic hydrocracking process and seeing how we can affect carbon dioxide, the compressed CO2 will affect that process. So what is compressed CO2 doing within this reaction? Well, if we look at the hydrocracking of polyethylene, we see that compressed CO2 is going to be acting as a plasticizer here. So it's going to be increasing the flexibility of the polymer, as well as increasing its chain mobility. This is helpful for us as one of the major limitations we have within hydrocracking of polyethylene is that the polyethylene has a high viscosity within the melt phase, which will lead us to have some mass transfer limitations just due to that slow diffusion of the polymer to the catalytic surface. So due to this plasticization of polyethylene, we can see an increase in that chain mobility, which will reduce some of those mass transfer limitations that we had before. So this is our experimental setup. We start with adding our polyethylene and our catalyst into the PAR reactor. And we hold this PAR reactor at both a constant temperature and constant stir rate, with the thing we're changing being the gas environment as well as the total pressure of the system. So the different types of reactions that we'll run is a hydrogen by itself as just a baseline. And then we're going to add 2 different secondary gases to our system to be able to compare effectively what the addition of a secondary gas is doing. So we'll add the carbon dioxide, which again is acting as that plasticizer. We're hoping to see an increase in conversion and yield by adding that. And then we're also going to add nitrogen to the system, which doesn't have the same plasticization effect as carbon dioxide does. So it's going to help us be able to effectively look at our results and determine what is exactly the compressed CO2 doing. After this process, we end up with gas, solid, and liquid products. So we'll use different techniques like GCMS and GCFID to determine both the composition and the yields of our products. So what are some of the results that we found? Well, one of the major results we found is that compressed CO2 is going to significantly increase both the conversion and the yield of our polyethylene. So if we look here at these 3 bars in the graph, I know it's kind of busy, but if you look specifically at those 3, that's just our hydrogen and carbon dioxide system at 3 different pressures. And if you see the 6 megapascal system is the one that we actually see this increase in conversion and liquid yield. So it tells us that we're going to need a sufficient amount of partial pressure of carbon dioxide in this system to effectively achieve these results in the hydrocracking process. In addition, if we look at just that 6 megapascal system of the hydrogen and the carbon dioxide and compare it to that nitrogen system, we see in the nitrogen, we're remaining over with a lot of solid products in comparison to that carbon dioxide system, showing us that it's not just the increase in total pressure in the system that is going to be having these effects, but it's specifically the sufficient pressure of carbon dioxide that is increasing both our conversion and our liquid yield. Some more results we can look at is exactly what type of products are formed within this reaction. So if you look at the top graph here, that is just the hydrogen system by itself. And then below it, we have 2 different graphs of when we add a secondary gas of either the carbon dioxide or the nitrogen. And we see that when we have this secondary gas in the system, we have a shift towards the lighter hydrocarbon region, specifically within the C5 to C10 range, which is nice because that's the C5 to C10 range is going to be corresponding to that gasoline application that we're looking at. In addition, we see when we add a secondary gas to the system that the isomerization is going to increase. So when we have just the hydrogen only system, it's around 38%. But then when we have carbon dioxide in the system, the isomerization increases to 85%. And then in the nitrogen system, it's 76%. This is helpful because the branched hydrocarbons have a higher octane number, which makes them more desirable for our fuel applications. So in conclusion, some of the major things we've seen from this research again is that adding compressed CO2 to our reaction will increase both the conversion and the liquid yield. So when we look at it in comparison to our hydrogen-only system, the conversion is going to increase from 67% to 85.2%. And then when we look at the liquid yield, it increases from 34% to around 56%. We also see that when we add that secondary gas into the system, it will shift towards a lighter hydrocarbon region, as well as increasing the isomerization of our products. Overall, this highlights a good potential result for being able to convert these plastics into usable fuel products. So I'd like to take a moment to thank Dr. Moraes and my mentor, Nick, who have helped me a lot this year learn about this project, and I really enjoyed working with them. So thank you all for listening. And if anyone has any questions, I'm happy to answer now. Yeah, we run these at 200 degrees Celsius for these reactions and these results.
Try any different temperatures?
No, we keep it at 200 degrees Celsius. Mm-hmm. Here's one. Yep.
So you mentioned you use gas chromatography, FID, and TCD. Why you use specifically these two, and what are you measuring with these two? What is the difference between these two, and what are you measuring with those?
Yeah, so you're asking the difference between GCMS and GCFID?
I saw it TCD as well. I know that's the detector, but you said TCD and also FID. Yeah. Why do you measure? What is the difference between these two, and what are you measuring with those?
Yeah, so I personally haven't specifically worked with the TCD. I've done more of the FID interactions within labs. So I know how the FID is going to be looking at our liquid products and being able to identify the composition and yields of them. So I'm not really sure exactly the applications of the TCD specifically, as I've worked more with the FID myself. Sorry.
So the reason we used the two different kinds of detectors for the GC is because we'll have a mixture of products that won't show up on either detector. So for the FID, we have CO2 or nitrogen in the system. So if we want to quantify those after the reaction, we'd have to use TCD and kind of have a similar problem where some of the larger hydrocarbon molecules will have a poor response on TCD. So FID for those.
I think this is a really cool research topic. Did you do any TGA analysis to assess water content?
We haven't personally, and nope,
But
we haven't.
I'm just talking about the TGA analysis of the polyethylene that you're using before you reacted.
I don't think so, no.
Analyze for any like sodium, calcium, or other elements, metals at a time to see what's going on in the system? Or do you see that afterwards in the solid coke that's formed?
I'm not really sure how to answer that question specifically, but I think it's a good thing to possibly look at in the future, how that might be affecting it. Yeah.
Cool.
All right, our next speakers are Abby Peters and Carly Barlows.
Hello, thank you for being here tonight. So today we'll talk about absorption of PFAS using zeolites and how we're characterizing our zeolites after this absorption, as well as how we're improving the absorption process. So PFAS are per and polyfluoroalkyl substances, and they're dubbed forever chemicals because their strong carbon-fluorine bonds make them really durable and long-lasting. So PFOS and PFOA are some of the longest they're long-term use PFAS that we've had. They were developed in the 1920s. So we've used them for a really long time. And over time, we've developed and used more short-chain PFAS, which are actually more difficult to remove from the environment due to their higher polarity and solubility. So the EPA has started regulating these PFAS, and by 2029, certain chain lengths and compounds will need to be removed to specified levels in all public drinking water treatment plants.
So the reason that PFAS are so prevalent today is they are resistant to heat, water, oil, and stains, and are therefore used in many everyday items such as nonstick cookware, cleaning products, and firefighting foam, just to name a few. And because of this prevalence of PFAS, exposure is almost inevitable. This also results in PFAS being in our drinking water. So these two graphs show around America as well as the Kansas City area where PFAS have been found or expected to be found. So the blue dots on the big graph on the left shows where the tested levels of PFAS are above the proposed maximum concentration limit. And the purple sites are where military sites are found. And there are higher concentrations around these due to the firefighting foams that they use there that leaches back into the groundwater. So average PFAS concentrations have found to be around 21.4 nanograms per liter in the source water and only goes down to 19.5 after treatment, proving that the current treatment methods for removing PFAS or just general drinking water treatment is not sufficient for removing these PFAS. So PFAS have a negative impact on human health. They can cause several types of cancer, such as breast cancer, kidney cancer. They are harmful towards unborn children and cause developmental effects. They bioaccumulate in humans, meaning there's more intake than outtake of the PFAS. And it is estimated that 98% of Americans actually have PFAS in their bloodstream.
So currently we use activated carbon and anion exchange resins to treat PFAS in drinking water. However, neither of these are super selective towards PFAS, so they're taking in a lot of other compounds, which means that they have reduced bed life, and that leads to more frequent replacement or regeneration. Both of these methods or medias can be regenerated. However, that's not always the primary practice because of the lack of regeneration sites close to all of the treatment plants. And also it's not always efficient for every single media. Additionally, and both of these can have negative effects on the drinking water, such as leaching of heavy metals from the activated carbon. And anion exchange resins are highly environmentally impactful whenever you're producing them. So you do want to regenerate them to make it worth or equal to the environmental impact of these. So we are looking at zeolites for the absorption of PFAS from water, and zeolites are silica alumina structures, also known as molecular sieves, with selectivity towards molecules like PFAS through their surfaces, voids, channels into their pores. And so we found that zeolites can be regenerated and reused after PFAS absorption. And specifically, we're looking at CP814E, which is a hydrogen beta zeolite. And we've also found that we can modify these zeolites to improve absorption, such as through dealuminification and replacement with different metals. But specifically, we've been focused on ion exchange. And so whenever we're looking at how to test these zeolites for PFAS absorption, just kind of the background of what our work has been is that we mix the zeolite with a target concentration of PFAS solution in HPLC water, which is usually in the parts per billion or parts per million range. And then we allow that to reach equilibrium, and then we can sample that and find out how much PFAS was loaded onto the zeolite using HPLC or triple quad mass spec.
Characterize the zeolites and see how they're performing before and after regenerating them after removing the PFAS. We use a piece of equipment called the ICP, or inductively coupled plasma, and this allows us to detect and quantify our elements of interest. And for us, that is silicon, aluminum, calcium, and sodium. We want to be able to confirm the ratio of silicon to aluminum, as they are the main components in zeolites. And we want to make sure that the framework is staying the same before and after regenerating the zeolites. So before we can run the ICP, we have to create a digestion solution. And we use a bottle with a material called LDPE, low density polyethylene, to prevent any extra leaching of other materials that we don't want to detect in our ICP, since it does detect such small concentrations of materials. So first, before we use the bottle, we rinse it with RO water and soak it in 0.1% nitric acid for 1 week to reduce any other contaminants. And once the bottle is clean, we can create the digestion solution, which allows us to dissolve the zeolites so that the ions inside the zeolites can be measured.
So we add nitric acid to dissolve most of the components, and then hydrochloric acid and ammonium fluoride to create HF that is able to dissolve the silica. And then finally, we add phosphoric acid to solubilize the calcium. So the order actually matters and which we add first. So first we do the solid zeolite and then the RO water. And we want to do the water before the digestion solution, so we're not adding just straight acid to the zeolites. And we add our digestion solution and shake that for a while. And after that, we do our final dilution of RO water. So these are some of our results from the ICP. The silicon aluminum ratio showed to decrease about 1% over 3 thermal generation cycles. So for example, the 0 thermal generation was not removed any PFAS, and it's about the same trend for both PFOA and PFOS, the 2 different types of PFAS that we tested. On the other hand, the calcium aluminum ratio did not change very much and is pretty consistent. And we think this is due to the calcium binding to the zeolite.
So in some of our previous experiments, we've noticed that the absorption of KPFOS actually increased after regeneration from the next absorption cycle, but we didn't find the same increase in absorption after using PFOA. So we're thinking that the sulfur is depositing onto the zeolite and binding with the alumina within the structure and the free alumina to increase the strengths of the Lewis acidity. And this is actually helping us to increase our absorption capability. So now we're looking at testing the zeolite with sulfur to see if we can further improve this absorption. Specifically, we're looking at improving the absorption of the short chain PFAS, such as PFBS and PFBA, because in the past we found that the absorption is pretty negligible on this zeolite. So it would be really impactful if we can improve this absorption. So we first loaded the zeolite with sulfur using PFOS, and then we thermally regenerated this at varying temperatures. And then we could test and see if the absorption capability was improved. And so with PFOS, there was an improvement in the absorption of PFBS at higher temperatures, but we saw no change in the absorption of PFBA. So currently we're working on sulfonating the zeolites using a different solution of ammonium sulfate. And this is where we will be putting the zeolites in an ammonium sulfate bath and then regenerating it at different thermal temperatures. And we're expecting that we will see the best increased absorption for PFBS at 650 degrees Celsius for the regeneration, as this is where we are supposed to see the peak acidity strength for these sulfate sites. So overall, we've been able to use ICP to confirm that the silica alumina and calcium alumina ratios are largely consistent throughout our ion exchange zeolites, which we didn't specifically talk about today, but we are improving those, modifying the zeolites. So this was a method of ensuring that we're not harming the actual framework. And then we also were able to improve the absorption of short chain PFAS using sulfonated zeolites. So in the future, we want to work to include sulfur within our ICP methodology, as well as further increase this absorption of short chain PFAS using sulfur, and to determine where the sulfur is going and if it's sustainable for long-term use. And then we're also working on regeneration methods using NSF-approved methodology and in situ destruction of PFAS. So we specifically want to say thank you to Dr. Shiflett and Dr. Corbin for all of your help and guidance. And huge shout out to CJ for graduating this semester. Thank you so much for all your mentorship throughout these years. So thank you guys. And do you have any questions?
Consider using XRF instead of doing ICP to get the elemental analysis?
I think CJ, we didn't get to run the XRF specifically, so that might be a question for CJ, but we have considered.
Did you find one to be superior over another?
We found ICP to be superior to XRF because we could actually get the ICP done. The XRF, we had to rely on measurements from CEBC, which once the NUP left, haven't really been happening. So that's, and we were able to actually get pretty good results. We compared our ICP data to zeolite standards and mineral standards. So yeah.
Try doing ammonia TPD to figure out characterize the acid sites?
Yes, we have done that.
There being more acid sites potentially, but you put a hand waving.
Yes. So for the hydrogen and the calcium, we've done the ammonia TPD on that. And we find that the acidity changes. Acidity goes down overall when you add the calcium, but some of the specific peaks, and especially the ratio of some of the strength of the acid peaks changes. So we're trying to identify which ones are important, and then doing like purity and FTIR and some other probe molecules are on the list of things to eventually be done.
Hopefully a paper including that is coming out soon. So
What was that? No.
If you go back to your conclusions, it says like, so silica, aluminum, and calcium aluminum radius are largely consistent. What does it mean consistent? Like in terms of, I mean, percentage, or what does it mean consistent? Like,
I mean, the silicon aluminum ratio is at what it's supposed to be, like from the ZLS standards, like it's around 12.3 to 12.4. So that was the range we were looking for. Calcium aluminum, I'm not as quite sure, but I know that we exchanged the calcium for inside the zeolite, but we see that there's less of a trend with the calcium aluminum. That's what I meant by constant.
although your error bars are big, however, I think like in between 12.1 and 12.5, you can see certain consistency. Okay, so yeah, thank you.
Our next speaker is Celeste Rusinger. Looking forward to your talk.
Okay, hi guys, I'm Celeste Rusinger, and today I'm going to be talking about what I've been working on this semester, which is developing an alginate-based hydrogel experiment for food science applications. So first, why is it important that we incorporate a food science experiment into our chemical engineering curriculum? So it's very common for chemical engineers to work in the food and beverage industry. Some examples of companies that students have gone into, especially from KU, are Frito-Lay, General Mills, PepsiCo, Kraft, I think all of those types of companies. And so then within the food and beverage industry, it's also important to acknowledge that hydrogels can be used specifically to encapsulate flavors and nutrients, as well as create and modify textures. So the simplest example of this that I can explain is popping boba. So popping boba is very popular, especially right now, and it's used to encapsulate several flavors as well as modify the texture experience for the user. And so the popping boba market size within the US is expected to reach about 893 million by 2031. And it's also important to note that it's expected to reach about 4 billion globally by 2031. And then some other examples of how hydrogels are used within food science are they're used to modify textures. So for example, in like fat-free salad dressings, hydrogels are used to imitate the texture of a fat without actually being very fatty. So they're kind of just used to modify the feeling of the fat within your mouth. And then this is slightly less research, but it's a topic that I've found interesting over the past semester. Hydrogels are currently being researched to see how they could be used for supplements. So encapsulating nutrients like vitamin C and then delivering that into the body via hydrogels. And so then going off from that, specifically focusing on popping boba, there are a variety of different properties that affect a user's experience with food. So the first is the poppability of the boba. So this is physically how the boba pops in your mouth and the sensation of that within the popping boba. And then next, the flavor. So you can encapsulate multiple different flavors, sweet, savory, spicy, sour. Those all affect the user's experience with the material as well. And then additionally, the interior consistency. So basically how viscous the inside portion of the popping boba is, if it's more of a solidified gel or if it's more liquidy like you see within popping boba. And then next is the dissolvability of the boba. So how that outer shell kind of dissolves within your mouth throughout the process. And then going off of that, it's important when talking about popping boba to create and formulate a procedure for popping boba. So how I've been doing this within lab is I've been taking sodium alginate and a flavor, and I've been using Coca-Cola in lab this semester. And you mix those together, and we use a blender to make sure that everything gets very well incorporated and well mixed. And then we also create a calcium chloride solution. And I've been using 0.5 molar of calcium chloride solution, as well as 1 weight % of sodium alginate plus flavor. And then I've been using a pipette and cutting about 1 inch off of it. And this is just so that the popping boba are similar in size to that of the market currently. So that's about 4 to 4.5 millimeters. And then when you drop them in, there's an ion exchange between the calcium chloride and the alginate, which creates this kind of encapsulation of popping boba. And so going off of that, popping boba experiment was successful. So we do have these beads that were formed through the procedure that was on the past slide. And these beads are comparable in size to popping boba on the market. So like I said, they're about 4 to 4.5 millimeters in size, which is comparable to popping boba that you see at frozen yogurt shops or tropical smoothie. Right now, they have popping boba as well as bubble tea shops. And so now that we have this procedure that is able to create popping boba that's comparable in size, it's important that we're able to also measure a variety of variables. And so one potential experiment that I've been more so theoretically creating this past semester, I haven't necessarily got to test this quite yet, but it's using cure time to measure pressure. So we have varied cure times. So this would be using a rectangular geometry of the boba beads. And so we have an immediate cure time, which means that the beads would be put into solution immediately and then immediately taken out. And then a 30-second cure time. So the beads would be left in solution for 30 seconds and then taken out. And then a 60-second cure time. So the boba hydrogels would be left in the solution for 60 seconds and then taken out. And then in order to do the pressure measurement, one larger bead or potentially a couple of smaller rectangular beads would be put onto a scale, and we would use a beaker of water to measure how much water it takes for the hydrogel to physically pop, or we could use a ruler to measure how much the hydrogel shrinks down in the case that it were to not pop. And so going off of that, the popping boba experiment is simple, and it has several different variables that can be tested, and the beads have been proven to be comparable in size to the market, as well as there's a bunch of different variables that could potentially be tested, as well as the properties mentioned in my previous slides. It's also important to note that sodium alginate is super cost effective, as well as the flavors that could go into popping boba, like sodas, juices, coffees. And the experiment is also really fun, pretty similar to the pancake experiment used in 112 right now. It's just another food science application that could be introduced into our curriculum. I just wanted to take some time to thank Dr. Bertuccio, as well as the Bertuccio Research Group and WISE for helping me with this research and allowing me to present it today. And thank you guys for listening. I'd be happy to answer any questions.
So why did you choose sodium alginate and no other, compounds? And what is some problem that you encounter while you are doing the experiment, or like the replication of the experiment, or I don't know.
Yeah. Okay. So specifically sodium alginate, just because it is so cost effective and it's just worked in our lab. I was recently doing drug delivery last semester, and I would do the same kind of formulation for the hydrogels that we use for our model drug. And it's just worked for me in the past, as well as it's just very cost effective. So that's currently why we picked sodium alginate, as well as when I was researching like formulation for popping boba. They also use sodium alginate in industry. So that's specifically what I was using it. And then I would say the main problem that I encountered this semester was figuring out how to get beads comparable in size to popping boba on the market. Because originally I was using a dropper method. So we had I was originally using a pump method and then I moved to the dropper method. And the pump made very consistently sized beads, but they were a lot smaller than popping boba on the market. So I found it a lot more difficult to get the interior pattern to be more liquid versus it was more of a gel with the smaller beads. And then to kind of counteract this, I decided to take a pipette and I cut an inch off of it. And this led to like a larger diameter for the beads to drop out of. And so it resulted in larger beads that were closer to 4.5 millimeters, which is a lot more comparable to popping boba in the market. And then in the future, I'm planning on buying a different sort of pipette or dropper that I can maybe use within the pump method as well. So I'm getting very consistently sized beads every time when I do this experiment, but that's just what I found as a solution for this semester. Yes.
Say you've got varied cure times. You get immediately 30 seconds, 60. You've got like a little container with what, probably 200, 200 beads in there. You've got to drop them in like one at a time. So you drop one in and take it out and drop another one in. Like when is the 30 seconds measured from? Because you got to drop them in sequentially. Do you take wait until they're all in and then wait for 30 seconds?
Yeah. So yeah. That is a very good point. That is something that I've also kind of need to figure out how to maybe combat. But what I've been doing is I'll let them drop for usually a minute. And then after that, I'll take the start time. So I'll like use the pump or I'll use my pipette and I'll drop beads in for 1 minute. And then I'll start the 30-second timer or the minute timer, or I'll take them out immediately after that. But that is a very good point, and that's something that I should work to combat in my lab in upcoming semesters.
I have a
Oh, I just do it for 1 minute. I just drop. Yes.
When you varied the concentration of the calcium chloride solution, did you notice a difference in I'm guessing I guess that's the resistivity of the bubble to pop? Or what kind of pressure are you calling that?
I would say I've just been referring to it as poppability, which is just not a super scientific term. But yeah, or in the case that it doesn't pop because it's more gel-like, it's just kind of how much it depresses. But based on the variation of the calcium chloride solution, if you have a higher molarity, the outside of the bead tends to be a lot stronger or a lot thicker. So it'll sometimes make the inside a lot more solidified rather than liquid whenever you have a lower molarity. But I haven't tested that personally a lot in lab this semester. I was more so just figuring out an experiment that could work and be tested with numerous variables, but that's definitely one variable that I plan to look into in future semesters.
What's the range, or what's the PSI or millibar that you get before it pops? Just curious.
Yeah, this semester it was more so qualitative for me, so I was kind of just popping it like with my fingers. This is more of a theoretical experiment. I actually haven't gotten the chance to test it in lab yet. I recently formulated this experiment over the past couple weeks, but yeah, just basically the longer they sit within solution or the higher the molarity of the calcium chloride, the harder they are to pop. So the lower the molarity of the calcium chloride or the lower amount of time that they sit within solution, the better they pop. There's more liquid inside. Yeah.
All right, our next speakers are Madison Jones and Samantha Hazel.
Hello, everybody. I'm Samantha, and this is MJ. And today we're going to be presenting on the separation of azeotropic refrigerant mixtures using ionic liquids. So here, oh, no, it's the same one for every presentation. So the main motivation for our research is to assist in the phasing out of high GWP refrigerant mixtures, GWP meaning high global warming potential. So one promising approach is the use of ionic liquids to separate these refrigerants. Ionic liquids are composed of a cation and an anion, both of which are tunable, which allows their properties to be tailored for specific applications. They have negligible vapor pressure, which minimizes solvent loss. They have high thermal and chemical stability, and they also have the ability to dissolve a wide range of compounds. Ionic liquids can exhibit selective absorption of certain refrigerants, which means we can potentially design ionic liquids to preferentially absorb one component of a mixture, which allows for a separation. The cation and anion that are highlighted over on the left complete the structure of the ionic liquid that we focus on in our research right now. It's known as EMim PO2F2.
That's based off of the differentiability and the peaks that we see. And then once we see that the peaks look good, and we have some examples of the graph on here, we can decide if further testing would be worth it on the IDA, which is the second part of our research goal. So once we, oh sorry, hold on. There we go. Once we determine that the ionic liquid is full and test this at different temperature and pressure points on the IGA, and then also determine solubility data, separability, quantify the diffusion coefficient of the refrigerant in the ionic liquid.
So the first methodology we're going to be covering is the gas chromatography method. So basically what we do is we create a solvent mixture. What we have been using is a 10-to-1 mixture of methyl hydroxide and dichloromethane. And so we mix the solvent with the ionic liquid, and then we coat the capillary column at a constant rate. So in the gas chromatography approach, the ionic liquid is coated onto the inner walls of the capillary columns onto the fused silica surface that you see here in the cross section. We do this by dissolving a determined amount of ionic liquid into a solvent and then administering it throughout the entire column. So when a refrigerant passes through the column, its retention time depends on how strongly it interacts with the ionic liquid. So a weaker interaction leads to faster elution throughout the column, whereas a stronger interaction leads to a slower elution and therefore a longer retention time. By comparing retention times, we can qualitatively assess selectivity between components. And the advantage of this method is that it is fast and high throughout the entire column, which makes it useful for screening ionic liquids to identify promising ones quickly and efficiently. So here's our experimental setup. So we take the column that we coated with the ionic liquid and the solvent, and we attach it to a constant pressure pump. And then we put it into a constant temperature water bath, and we wait for all of the solvent to evaporate. You can see the interface as it goes through the column. So once the interface is all the way through, then we can go ahead and take it out. And then we put it into the gas chromatography machine. So we take a bit of a sample of whatever refrigerant we want to run through the ionic liquid, and we insert it. And at the same time, we start the data collection for the gas chromatogram, which we can then see on the computer in real time. So these are two examples. These are hypothetical. These are not real results. The results that we've gotten so far pretty much just show one peak. So we're trying to separate them. So the one on the left would be a really ideal solution. Each peak is 2 minutes apart. So that would be really amazing for separability. And then the one on the right is something that wouldn't be as preferable because the peaks kind of run together. So you can't really tell when one separation starts and finishes. So that would not be ideal. So one of the main challenges we encountered with the column coating is incomplete solvent removal and air bubbles within the column. Both of these prevent proper film formation and reduce efficiency. You can see an example of incomplete solvent removal in the image on the left. There are large bubbles which indicate a leak. This prevents us from testing these columns in the GC. To address this, we are optimizing the coating process by adjusting the solvent system. This includes going from a combination of methanol and DCM to just pure DCM, as it is a less polar and more volatile compound, which allows for a more controlled evaporation. After we fixed leaks in the vacuum setup, we were still seeing issues like solvent flowing throughout the column, so removing methanol was a logical step to improve the solvent evaporation. We are also trying to lower temperature and vacuum conditions, as less polar ionic liquids may be sensitive to uneven solvent evaporation during the coating, so it's better to just do it low and slow. You can kind of see differences in the second picture where the bubbles are much smaller. They could indicate a leak, but the fact that the bubbles are not in a straight line could also mean that there is a coating present, but maybe it's just not as uniform as we want it to be.
Better known as the IGA, to measure gas absorption into ionic liquids. So this instrument is able to track very small changes in mass as a gas is absorbed at different controlled pressure and temperature conditions. So we have the, hold on, let me do this. We have the counterweight on one side of the IGA, which balances the weight of our sample mass in our sample bucket. And then on the other side is our sample bucket. And then our sample bucket is degassed at 75 degrees Celsius in high vacuum to remove moisture and or volatile impurities from our sample. And then once the mass is stable, the isotherm can be started. And from the measurements we get from the isotherm test, we can determine equilibrium solubility as well as diffusion coefficients. And this provides a more quantitative understanding of thermodynamic and transport behaviors for the interactions of ionic liquids and refrigerants. So for example, from solubility measurements, we can determine the selectivity differences between refrigerants. We can calculate diffusion coefficients to assess mass transfer behavior, and then we can further study ionic liquid refrigerant interaction through structure property relationships. So this graph, these two graphs are examples of data that we have from R125 and from R34 being tested. I believe this is PO2F2 for both of these. And then as we can see on the graph on the left, we're seeing, hold on, hello? Okay, these green triangles here are at 25 degrees C, and that line there shows the better mass fraction that we're seeing for R125 compared to R32. So for this specific ionic liquid, we would determine that R125 is more soluble in it. And then we can also determine diffusion coefficients from this. And, oh, the ratio we see of R125 to R32 solubility at 1 megapascal for 3 different ionic liquids, and this is at varying temperatures. We see that at 25 degrees C and with PO2F2, we have the most preferential solubility at R125. And then in addition to solubility, diffusion is also important for the separation process. And then the diffusion coefficients we see on the table on the bottom for PO2F2 based ionic liquids, they're on the order of 10 to the negative 9th and 10 to the negative 10th, with are significantly higher than the diffusion coefficient orders for PF6 based ionic liquids. And then this is also in line with the viscosity of both of the ionic liquids, so the PO2F2 and then the PF6. And the PO2F2 ionic liquid has a lower viscosity than the PF6, which viscosity will be inversely related to our diffusion coefficients. So that 10 to the negative 9th and 10 to the negative 8th being higher results, or not results, but like compares to our lower viscosity we see. And then this indicates a faster mass transfer, which is beneficial for the process performance. And then we also observed that diffusion increases with temperature, which would be expected. So yeah, in conclusion, for the tests that we've done this semester, we have learned much more about the new ionic liquids we have by using both gas chromatography methods and methods on the IGA. And then we found higher diffusion coefficients with our PO2F2 ionic liquid, which related it to the faster solubility. And then the PO2F2 showed the best potential for separation of R125 and R32. And then what we'd like to explore and research more in the future is optimizing column coating techniques. And then we'd like to run more tests on the GC with individual refrigerants to see if we're like actually getting peaks and if the ionic liquid is interacting with that refrigerant. And then we want to run tests with refrigerant mixtures and see how well those mixtures are splitting based off results on the chromatogram. And then we want to test separation abilities of new ionic liquids on both the GC and on the IGA, and then test ionic liquid separation abilities with new refrigerants. And yeah, we'd like to thank Dr. Shiflett and Claire, who unfortunately can't be with us today, but for their help with this entire project and their mentorship and just being there to guide us through this process. So yeah. Any question? Yeah.
So I have a couple of questions for you. So as you're doing these experiments, you showed like your representative chromatograms. And so I'm assuming with those chromatograms, that's assuming you have multiple components running through. Okay.
Refrigerant mixture.
Okay. And so when you're doing your preliminary testing, you're only just running one refrigerant at a time?
Yes.
Okay. And eventually we want to try and get those chromatograms that you were showing.
Yeah, we're trying to find an optimal ionic liquid,
Okay.
and then we'll start testing more refrigerant mixtures.
Okay. And then as you're showing your results with the diffusion coefficients, running it through the gas chromatography column, how do you back out the diffusion coefficient? Because I don't know how to do those calculations. So
Those calculations are all done in Excel. So that's just for us. Claire has like an Excel table, and we just have like I like copy and paste the values from the like experimental data we get after running the IGA into like a set of like different cells in Excel, and all of that's done for us. So I haven't really looked that much into it because at least for like Samantha and I, that's just something Claire like, I don't know, she just tells me like, hey, plug this into my Excel. So I don't really like, I just kind of do that for her. If she were here, I'm sure she'd be able to say a lot more about like, oh, this is more about the diffusion coefficients, but I don't really know much.
Curve of mass uptake as a function of time. You can fit that with a one-dimensional diffusion equation. And then from that, you can calculate the diffusion coefficient. And then when that levels out, that's the solubility value. And you can do that at each pressure and temperature. So Claire provides them with the data, and then they fit it and look at the fit and calculate the diffusion coefficient. Yeah, one-dimensional is assuming that like you've got this container and you can do a separation of variables, and you've got basically a flat surface, and you're assuming the gas is diffusing down through this cylinder. And then from that, you're calculating the diffusion coefficient. They do, and you know, that probably affects it a little bit, but it's not much though. You know, I think you got a little meniscus on each end, but the middle is kind of flat. So we've taken that into account sometimes, and I mean, it doesn't change the diffusion coefficient very much, maybe 5%. Other questions? So one question I have, you know, the columns you guys have been coding are about 5 meters. Do you see, could there be any, is there a possibility that you could coat longer columns? Let's say like we wanted to coat a 30-meter capillary column. You think that's still possible?
Last week was finding longer capillary columns to test. So that would be something we would be able to do in the future, or at least just see like if that would actually work. But from what she was saying with her preliminary, gosh, sorry, it seems that that should be possible, and that the 30 meters in length should show some better signs of, I guess, separation, like just having that a longer like length to go through.
So like a 5-meter column, how long does it take before you see material come out the other end? Seconds. So
it pushes at like a very steady state. So like 15 to 30 seconds is until we see like the liquid exiting on the other side.
Right now is we're using DCM as a solvent, and so it's just a very strong solvent, so we don't feel comfortable using like different materials than what we've been using.
Also, for the ionic liquid, like absorbing into the silica, we kind of want it to like sit on the walls of the silica, which is why we like vacuum it so that all of the ionic liquid does like absorb to the walls. But I don't believe there's any like properties cohesive with silica that would actually have it like absorb into the silica rather than just like sit on the surface of it. So
all right, our next speaker is Greta Hines.
Hello, everyone. My name's Greta, and today I'll be presenting my research on developing a reproducible emulsion formulation for undergraduate instruction on complex fluids. An emulsion is a mixture of two immiscible liquids with one liquid finely dispersed into the other. Because oil molecules are nonpolar and water is extremely polar, they cannot form a uniform, homogeneous solution. Instead, it separates into two distinct layers, as shown here. In order to combine them, a process called emulsification is required. A process where an emulsion breaks down one liquid into tiny droplets, which then become spread throughout the other. Emulsions are especially useful in formulations because it traps active ingredients inside these microscopic droplets, which then protects sensitive compounds from degradation. It helps control their release and keeps them effective for longer periods of time. Emulsions are extremely widespread through many different industries and are commonly found in many consumer products. Milk is an excellent example of a natural oil and water emulsion, as small fat droplets are dispersed evenly throughout water. In milk, natural proteins act as emulsifiers, which coat these fat droplets and prevent them from clumping together. In consumer care products and cosmetics, emulsions can improve hydration, stability and shelf life, enhance skin feel, and versatility in product design. In the bioprocessing and pharma industry,
Many vaccine and drug delivery systems utilize either nanoemulsions or lipid emulsions in order to transport hydrophobic drugs, which are then distributed out into an aqueous phase. Controlled droplet size means controlled release and bioavailability. The more effective delivery system we have causes fewer production resources that are needed per treatment. These formulations are oftentimes used in larger companies such as Pfizer and Moderna, two companies I'm sure you've all heard of. Okay, additionally, emulsions are extremely relevant in the sustainability industry. The first being biodiesel production, which relates directly to the renewable energy and fuel industry. Water and diesel and biodiesel emulsions significantly improve combustion efficiency. Microexplosions occurring during combustions provide for a better atomization. It also works to lower the particulate emissions and provides for a more complete fuel burn. So the overall sustainability impact we're seeing is cleaner combustion, it's enabling the use of lower grade biofuels, and it reduces overall air pollution. The second sustainable industry emulsion relevance is found in is enhanced oil recovery using polymer emulsions. In chemical EOR, engineers inject a surfactant polymer emulsion into reservoirs, which then mobilize trapped oil droplets that flooding water cannot remove. This creates microemulsions that continue to flow through the rock pores, and it improves the overall energy efficiency per barrel of oil that is recovered. Okay, a surfactant or a surface active agent is extremely crucial in having an effective emulsion process. The amphiphilic structure of these allows it to form a physical barrier and allows the emulsion to even occur and prevents oil droplets from coalescing together. The way in which it stabilizes an emulsion is by reducing the interfacial tension between the two phases, which lowers the forces that keeps them apart. This nature causes them to migrate towards the interface. At these interfaces, the surfactant molecule aligns itself with the hydrophobic tail pointing away from the water submerged in oil and the hydrophilic head surrounding the water and pointing directly towards the water. This disrupts all the surface tension and allows liquids to spread more evenly and penetrate through more surfaces. Okay, so there are two main mechanisms of stabilization within an emulsion that are both extremely relevant and significant in having an effective process. The first being steric hindrance. Steric hindrance occurs when large molecules, such as surfactants, adsorb onto the surface of molecules and extend outwards. Extensions form physical, hairy, or thick layers that extend onto the droplet surface. So when two droplets approach one another, those absorbed layers overlap, creating a repulsive force that prevents droplets from coming in contact with one another and aggravating. The second method we see here is electrostatic repulsion. Electrostatic repulsion occurs when droplets are carrying like charges on their surfaces. These ionic surfactants counter-attract ions and create an electrical double layer. Okay, so this experiment evaluates emulsion stability by tracking how quickly an oil-water mixture separates over time. As we can see here, at time equals 0, the system is a fully mixed emulsion. And as time progresses, we start to see some separation within our solution. And over time, the droplets begin to fully coalesce and a distinct oil, mixed, and water phase is formed. We then measure those 3 phases and including the total emulsion height. We then use those 3 phases that we measured in order to calculate the percent separation, where we take the height of the water phase plus the height of the oil phase and divide it by the total height of the emulsion. This specifically quantifies exactly how much of the emulsion has broken down or broken apart at each time point. Being able to compare separation curves With different surfactant concentrations, we can determine exactly how effective each formulation is at preventing coalescence and maintaining a stable emulsion. Additionally, these calculations help us identify the optimal surfactant level in order to minimize separation, supports product stability, and maintains uniformity over shelf life. Okay. This slide compares two different surfactant concentrations and data from them. The first being sodium dodecyl sulfate, which is a strong anionic surface, shows rapid and nearly complete separation at high concentrations under a short period of time. There we are. Okay, so it's showing its complete separation at higher concentrations in shorter periods of time, which is indicating that it aggressively disrupts droplet interfaces and speeds up coalescence. In contrast, lecithin is a naturally derived phospholipid emulsifier that produces slower and less complete separations over the same amount of time, which reflects its stronger interfacial behavior and stronger stabilizing film protection. Together, these profiles exhibit exactly how surfactant type and concentration directly control emulsion stability. Okay, so despite this experiment still being very early on in the development of it, this is an extremely viable experiment for future uses, as it's able to take a theory and put it into a hands-on experiment with real data and understand fluid applications and complex fluids for specifically undergraduate instruction. Okay. Thank you. I would like to give a huge thanks to Dr. Bertuccio and the Dr. Bertuccio Research Group and Courting the WISE organization for putting this together and allowing this opportunity to happen. Thank you. Any questions?
I have a question. How did you determine your concentrations? I noticed like the lowest concentration was 0.25 and maybe the highest was around 15. What guided you with the concentrations that you chose and the range? And have you thought about using even lower concentrations or higher concentrations?
So yes, we have definitely thought about using lower and higher concentrations, except we have to be careful of a certain level so it doesn't surpass the surfactant like stability. And the way we measure that is essentially just measuring out in a certain like milliliter or centrifuge tube is mainly the way that we're measuring out those concentrations.
So to add in, so right now, since it's the early stages, we're really just exploring a lot of different concentrations, and we're aware for a lot of uses of surfactants, it's usually a low concentration, probably like 0.1 weight percent or a lot lower than that. For the sake of right now, just because we're trying some surfactants that aren't necessarily the best ones, for example, SDS is more like for cleaning purposes, we know that we probably need to jack up the concentration if it's going to have like some emulsification properties. Down the line, yeah, we'll definitely try to find like more ideal surfactants that are consumer or industry relevant and hopefully are lower concentrations as well, just so you don't have to run through as much stuff. But for now, we really just want to show like, yes, it can work in a reasonable period of time.
So what does it mean that at 15% weight percent, your trend is very, very apart from the other set of data points, you know? All of them follow a trend that is very speed, and the other one it's not. And there are also some, I guess, missing information, or no, it's not missing information, but between 6 and 10, there is kind of like no data points. So why is it that, and why is so different than the rest of the data points?
I think that's definitely a way that we just picked out certain concentrations from the surfactants, because like Dr. Bertuccio said, we're still kind of figuring out exactly what concentrations would work the most efficiently in our emulsion. So therefore, we want to kind of try to find a decent range of concentrations to test. And you asked about the 15 weight percent. That is just showing that over less time, there's just more percent separation coming from that. So I think those are values that we picked that we thought would be the most efficient overall in the experiment.
Well, yeah, I'm just going to add in with the nature of these experiments, they're right now just visually looking at the separation profiles. And so it's not necessarily the easiest to see where exactly the layers are. And so some of the data may look a little wonky just because it's not the easiest to differentiate where the oil versus like the emulsified layer versus the water layer is. Yeah. Yep.
So as we go on with the experiment, we're kind of narrowing down the best, most effective ways to measure each surfactant concentration.
All right, our next speakers are Carson Welbrock and Evan Denard.
All right, so this is on, right? All right, good evening, everyone. Hello, my name's Evan, and today we're going to talk to you about what we've helped work on over these last 4 months. So it's adsorbent screening for refrigerant R410A separation. So here's just a bit of a rundown of the itinerary for this evening. We have the problem that we're trying to solve, our objective of what we can do, our methodology of going about doing that, as well as some of the results that we've gotten from that, and then just some analysis of the results, and then our plan for the next semester going forward. So hydrofluorocarbons, or HFCs, are currently the most common commercial refrigerant used. However, there are some environmental concerns with those, such as the global warming potential, which can be several hundreds or even several thousands of times higher than that of CO2. So there's a need to reclaim and then recycle the components within those mixtures of refrigerants. However, like I said, since they're refrigerant mixtures, in order to recycle them, okay, to solve problems of the previous generation. So the goal of our research is to separate the R410A into its individual components by adsorption. So what we're doing is we're screening many porous materials that can do that adsorption, to determine which ones are most effective at separating the R410A into its individual components of HFC32 and HFC125. So some of the materials that we're testing include MFI zeolites, beta zeolites, silica, as well as activated carbon. So as for our methods, this is a picture of the apparatus that we're working on. What you can see there wrapped in the insulation, that's the test bed. So what we do first is we pack that with the material that we're looking to screen the separation properties of, and then we leave that overnight to pre-treat at 250 degrees Celsius. So then the next day, we introduce the R410A mixture into the system by turning on the mass flow controller. And then that R410A flows through the column packed with the material. And then a mass flow meter will monitor the flow rate of the 410A. And a mass spectrometer will tell us the percentages of the HFC 125 and the HFC 32 that have been separated that are leaving the bed. And then from there, a computer can take that data and create a breakthrough curve that we can read to see how effective the separation was.
As Evan mentioned, the mass spectrometer is going to plot a breakthrough curve for us. That can be seen on this left-hand graph. So the solid green line is going to represent HFC 32 coming out of our system. And then the dotted red line is HFC 125 coming out of our system. So the important thing to note here is that HFC 32 is coming out minutes before the HFC 125. And this gives us a separation window where we're getting pure HFC 32 and no HFC 125. So the goal is to make this separation window as large as possible. That way we can recover the most pure HFC 32 possible. And then on this graph on the right, we plotted our mass normalized separation window against the silica to alumina ratio of the MFI zeolites that we use. And as you can see, as the silica to alumina ratio increases from 16 to 26 to 181 and all the way up to 500, the mass normalized separation window also increases. So this tells us that as we increase the silica to alumina ratio, we can expect our separation window to increase as well. And from there, we determined that as we increase our silica to alumina ratio, the selectivity towards HFC 125 would increase. And that can be seen on this curve on the left. And then on our right-hand curve, we plotted all of the adsorbents we screened this semester. So all of the black dots are MFI zeolites. The blue one on the bottom is a silica. We have a green dot representing an activated carbon. And then the red dot above is a beta zeolite. So as we increase vertically on this graph, we're increasing the amount of pure HFC 32 we recovered from our system. And then as we increase to the right, we're improving our selectivity towards HFC 125, which we calculated at saturation. So as you can see, the beta zeolite CP811C and the MFI zeolite TS1 are looking like very strong contenders for this adsorption process because they give us the most pure HFC 32 recovery. To kind of wrap up and state our key points here, we found that as we increase the silica to alumina ratio in our MFI zeolites, we also increased the separation window. And from there, we were able to, I guess, as we increased the SAR, the MFI zeolites also increased in selectivity towards HFC 125. And then perhaps more importantly, we found that the beta zeolite CP811C and MFI zeolite TS1 are our strongest candidates, or I guess most efficient candidates per gram at separating or recovering pure HFC 32, excuse me, sorry. In the future, we want to screen more adsorbents and analyze how increasing flow rate changes our system, because that's going to bring in its own set of challenges, and so we'd love to investigate that further. I'd like to thank Emmanuel, Dr. Andrew Janssen-Jardin, Professor Shiflett, and Dr. Corbin. That's all we got. Thank you.
All right, any questions?
have any theory as to why the silica to alumina ratio is changing things? If it's not changing the pore size, what is causing that effect to happen?
So increasing the silica to alumina ratio of the MFI zeolite is basically making the zeolites more hydrophobic. And there's another data that they should have shown. The HFC 125 is having a very a higher polarizability compared to HFC 32. So that being said, the HFC 32 is also having a higher dipole moment compared to HFC 125. So the HFC 32 is more attracted or has a higher affinity for a polar zeolite with a higher polarity. So making it hydrophobic means that it's going to interact more better with HFC 125. Yeah.
And our final speaker for this evening is Jack Kellogg. Come on up, Jack.
Okay, hey everyone. My name is Jack Kellogg, and for my research that I've been doing the past 2 semesters, it is the selective reduction of N-butyraldehyde over isobutyraldehyde using YADH as an enzyme. So yeah, table of contents, pretty straightforward, same as everyone else. So for our objective, our main motivation in this research was finding a way for separation, as it is a major issue in industry. Specifically with aldehydes, aldehydes are a very tricky chemical substance to separate, mainly due to their similar boiling points. And although regular distillation is a viable method for separating, it proves to be a very expensive process overall. So naturally, we wanted to find alternatives. And as a result, using a substrate enzyme separation method was what popped up in this instance. So in this situation, what we wanted to employ with this substrate enzyme method was oxo processing, otherwise known as hydroformylation. Now, with hydroformylation, it mainly involves using carbon monoxide and then hydrogen, and then reacting those with propylene to turn each into an identifiable isomer of aldehyde, in this case, isobutyraldehyde and N-butyraldehyde. With both these substances, they are very distinct in their chemical formation. Isobutyraldehyde being a more branched substance, while N-butyraldehyde is a much more linear composition overall. So in the instance of an enzyme substrate process, our hypothesis was that YADH would be much more selective in acting as an enzyme towards N-butyraldehyde due to its linearity, as opposed to the branched structure of the isobutyraldehyde. So for our methods of experimentation, we started out with trying to analyze the concentration of our aldehydes. We used GC to assess this, as well as UV vis to analyze both our substrate and YADH. In this instance, NADH and YADH, respectively, for the substrate and enzyme. We measured our substrate at 0.4 millimolar for this experiment specifically, our YADH at 0.00 milligrams per milliliter. And continuing on, we tried to analyze 6 samples, all pertaining to one trial, of increasing concentration values of our inhibiting aldehyde, ranging from 5 millimolar to 100 millimolar. And in this setup, we would use Beer's law to calculate a concentration of NADH over time in a 3 milliliter sample of our solution and examine the conversion percentage and subsequent binding potential of the NADH to NAD plus reaction with both aldehydes and compare. For our model that we decided to use in this instance, we looked to the Michaelis-Menten equation with substrate inhibition. This model theory proposed that as the aldehyde concentration increased, our overall conversion percentage would decrease in regards to the YADH to NADH binding reaction. And in this instance, we had our Kcat as the catalytic efficiency of our enzyme. Our Km is the binding affinity of the aldehyde, measuring that strength of the binding itself, and then the inhibition constant of the aldehyde on the enzyme as Ki. A couple results that we had in our graphs. We found that the NBA reaction was very fit for this model theory. It was almost very exact in its modeling. And for our Kcat, we had a much higher value of 1,400 as opposed to our isobutylaldehyde value of 42, measuring that total strength being much greater in MBA as opposed to isoBA. For our Km, both species were very smaller in that regard, but as opposed to NBA, our isobutylaldehyde inhibition constant was much greater than the NBAs, which primarily meant that that binding strength was very low, pretty much canceling out the aldehyde's ability to inhibit that total reaction and inhibit it as shown on the left graph as that concentration slowly starts to decrease. So for our future work and assessing this, we will try to employ characterization techniques like CD spectroscopy, which will assess conformational changes that the enzyme will go through in the presence of these aldehydes, and other methods that we might use include computational work such as molecular docking, and we will probably work in tandem with the Department of Chemistry to solve those. In conclusion, we employed enzyme kinetics to validate our hypothesis that our enzyme YADH prefers N-butyraldehyde over isobutylaldehyde. We observed a lower catalytic efficiency for isobutylaldehyde as opposed to N-butyraldehyde, and this proved that our modeling was more inaccurate, as it referred to, for isobutylaldehyde due to a non-decreasing steady trend line that never showed any plateau before it started to decrease at all. So we will probably need to find a better fit model for that. But yeah, a couple of acknowledgements, I'd like to thank the School of Engineering, Dr. Allgaier, my mentor, Pratusha, and everyone else in the Allgaier Research Group for their continued support. And yeah, thank you all for listening.
So yeah, I saw your like characterization setup and everything. But I assume you have like an actual like reaction vessel.
Yeah.
Did I missed that, or like could you just talk about your actual like reaction vessel?
I mean, we mainly just used cuvette samples for the 3 milliliter solutions we made for that, increasing reaction with multiple different concentrations. So, yes. And then we plug it into GC, or not GC, UV vis to analyze that decreasing absorbance that would happen over time. Yeah, so I mean, it's mainly just kind of like more refining that a bit more, but this is pretty much the end of this whole experiment as it relates to the whole project. But yeah, like I said, there's additional modeling that we could probably try to do using more technical methods like molecular docking and other things. So it's mainly just about refining that and making sure it's good enough to put out in a paper. So.
Well, thank you for hanging in there with us. And I do have some thank yous that I'd like to go through. First and foremost, I'd like to thank the Wonderful Company. The Wonderful Company is the one who provided us with the funding to start the Wonderful Institute for Sustainable Engineering. And we use those funds for supporting undergrad researchers and events like this. So a big thank you to them. Some of them actually may be online. And I'd like to also thank the folks that are online. I know we've got several that watch this from other states. I think Pennsylvania is represented, North Carolina, and California. So I'd like Lacey maybe to come up front. So a tremendous amount of planning goes into this. And so I just want to thank you for all of your help. This was a fantastic event. I think it's probably the best one we've done. I mean, we've been doing these now for several years, and every year I say the same thing, that I think it's the best one we've ever done. But honestly, I think this is the best one that we've ever done. So thank you so much for all your help. You know, Lacey starts planning this, you know, months in advance, and it takes, you know, a lot of effort to pull all this together. I also like to thank Tiffany. I think she might still be out in the hallway, but she also took all the photographs. And I'd like to thank Emily also for helping organize this event. So Lacey, Tiffany, and Emily, thank you guys so much. Also like to thank the volunteers. So I know Berlin went and picked up food. So thank you, Berlin. Abby and Evanna and Julia for decorating. And Univa and Tom for handling the microphones and the Q&A. Also, the catering was from Taco Zone. So we brought Ziploc bags. They're in the back. And there's still plenty of food. So please make yourself a taco, put it in a Ziploc bag, take a soda, put cookies in a Ziploc bag, do whatever, but please take some of the food home with you. I'd also like to thank Cody Howard from the School of Engineering. He was here earlier taking pictures, and you're probably going to see yourselves in a couple different venues online. Watching the presentations, like the graphics were amazing. Like I'm almost ashamed to put my PPTs up. Like you guys, the graphics were amazing, and also the speeches, right? Like I was thinking about when I was an undergrad, I couldn't do this. I couldn't have got up here in front of people and spoke, And so some of you are first years, some of you are, your final year, but just amazing presentations and work. So I'd like to just finish up with, good luck on exams. I know it's a busy time, but good luck next week. Have a wonderful summer. Some of you will see during the summer, but probably most of you we won't. If you're graduating, good luck. If you ever decide you want to come back and get a master's degree or PhD, let us know. We'd love to have you back. Yeah, for those of you that are coming back, we'll see you in August. Remember the food in the back. Safe travels, and that concludes our evening. And yeah, good night.